challenges and okay. So today we'll be hearing about the cold food chains, their challenges in developing countries and possible solutions that we can have from different technologies that STFC provides, but also the in-house, the indigenous technologies that we have in those countries. Our first speaker for this webinar is Brian Shaughnessy from RAL Space STFC, and he would be presenting about considering space thermal technologies to improve portable cold storage for foods. So over to you, Brian.
Great, thanks, Sanal. So let me get my presentation up and running, which worked a moment ago, didn't it?
It did.
It did. Now it's disappeared. There we go.
Brilliant. And if you can go full screen.
Just thinking about it. There we go.
Yeah, perfect.
Okay, so hello everyone. I'm Brian Shaughnessy. I run our thermal engineering group at STFC. Our work, day-to-day work, is designing thermal control systems for scientific space instruments and spacecraft. What I'm interested in is if any of this knowledge that we have can be applied to help in improving the food supply chain. We have a STFC Food Network scoping project to look at how we might apply our knowledge to improving cold storage of foods, but portable cold storage, so in the supply chain. So it's a collaborative project. It's a very small collaboration, but nevertheless a collaboration. I'm the principal investigator on the STFC side. We have an immense amount of local knowledge on food supply from Sarang Vaidya, who's works for Go for Fresh in India. So he has all that knowledge about actually what happens in real life. And my colleague, who I've seen during this call, Nifaraj, is our spacecraft thermal engineer. So he's doing most of the thinking and analysis for this project. So what we're doing is exploring ideas to improve portable cold storage. We're focusing on the tomato supply chain in India. It's contributing to sustainable food systems. And the key thing here, and the most important thing I think about the scoping projects, is it's combining interdisciplinary knowledge and expertise. I'll talk a little bit about what we've been doing, but the current status is we're bringing it all to a close. The project is in progress. We're completing thermal analysis, and we have, I think, a few weeks left to actually put it all together into a report. So by way of background, we know that food wastage is a major problem globally. In developing countries, and especially places where there are warm climates and people working in a large rural areas, a contributing factor could be the lack of effective cold storage. So basically you're trying to keep things cold because we know that helps produce last longer, but the environment is very warm. So we're trying to bring those two conflicting issues together. As I said already, the focus here is on cost-effective and efficient portable cold storage for tomatoes, and tomatoes is a great case study for us. I should really just mention briefly about what I normally do. This is a project I hope many of you are familiar with, which is the James Webb Space Telescope, which launched, I've got the date wrong as well. I should know this. It was Christmas Day last year. We at RAL Space did the thermal engineering for the mid-infrared instrument, which is shown in the picture on the right here. This is a scientific instrument that operates at -267 degrees centigrade, so very, very cold. It's just about as cold as you can get things. So we, although we didn't develop the cooler ourselves that achieves this, what we were responsible for was achieving the design that allows the cooler to achieve those temperatures. So if, for instance, we had too much heat being conducted into the instrument, we wouldn't be able to cool it down to the temperatures and it wouldn't be able to operate. So this thermal design, what we're doing is actually critical to the success of the mission. You know, if we didn't do our job properly, then the instrument wouldn't cool down, and we would have this huge James Webb Space Telescope observatory up there, which wouldn't be working as we wanted. So challenge for us really is, you know, here, you know, we want to apply this knowledge that we've gained from working on space thermal in projects into other areas. The approach we've taken for this particular project, this is a very small project. It really only amounts to a couple of weeks, maybe 3 weeks worth of work in total. The approach we've taken is pretty straightforward. It's a desk study. We establish requirements and boundary conditions. We run some investigations based on that, and then we produce a final report with some recommendations. We've chosen to do this by developing a very simple thermal model to understand sensitivity to different parameters that affect the produce temperatures. Based on this parametric analysis, we will then suggest improvements that are based on our own thermal design experience, and from that recommend follow-on activities. We're focusing on tomatoes here, and in particular the tomatoes in India. You know, India is one of the largest producers of fresh fruit and vegetables, and most of this is consumed fresh. Now, here in the UK, a lot of our vegetables are moved around in using the cold chain, so being kept cold throughout their journey from being picked to appearing on our shelves at supermarkets. And, you know, just going outside today, we know how nice and cold it is in the UK a lot of the time. In India, if the average temperature is, you know, easily into the 30s, yet, you know, so we think, okay, why not use the cold chain? But it's very limited in use in India. Tomatoes are a great case study. It's a widely grown vegetable, but it has a short shelf life and it's at high risk of post-harvest losses. I think that there are probably lots of desired temperature ranges depending on exactly what you're trying to do with a tomato and what condition that the tomato is in. But a good starting point for us is this 12 to 15 degrees centigrade range. Now currently, this is representative of how tomatoes might be transported after harvesting. They're stored in plastic crates, potentially actually in the open environment, so exposed to sunlight. These crates may often be covered with some paper, newspaper, or other materials to try and keep the heat of the sun off them. What we're looking at then is how, you know, what we can do that's really simple that can improve this and help the tomatoes stay colder for longer. So this is a schematic. I mean, it's clearly a schematic, but it's showing what we've been doing. I wouldn't read too much into this particular data. This is just an example of what we are doing. We have a very simple model where we have a crate containing produce. We have the heat from the sun. We have the thermal radiation that goes off to the sky, and we know that might increase overnight when it's colder. We also have the circulation of the air around it, so this hot air that could be up at 30 degrees centigrade. And this chart on the right shows an example of a thermal prediction over a number of days where we have produce. I'm hoping you can see my mouse, but we have a sort of a cyan line which stays relatively cold for a while and then starts warming up. And the reason it stays relatively cold for a while is because this particular simulation has an ice pack in it which stays cold for some time until it starts to heats up and starts to melt, and then everything increases in temperature. So this is representative of what we're doing. Like I say, I wouldn't read too much into what this means, because this is still work in progress and we're refining the details. So the possible design approaches we might take. Retrofit is nice, because that is something that hopefully is quick and easy to do without designing a new product, which might also be more expensive to implement. So things like covers, improving on this idea of having newspaper on the crates, or having an enclosure or cover for entire stacks of crates. We could look at more detail on insulated boxes and perhaps adapting the spacecraft insulation designs that we already use, so that they're better suited for use on ground. Having better insulation then allows you to use ice packs or cool packs more effectively. Another thing I'm really interested in is how we can manage the solar load that is on these crates, so it's the sun that shines on them, and the day-to-day temperature variation. We use a lot of, in space thermal engineering, of these selective thermal finishes, which can reflect away sunlight when you don't want it, or isolate from the cold night sky. There's also other, these are more complex solutions, but things like louvers, which it's best if I show you a picture actually of a spacecraft implementation here on the right, where these louvers, they're rather like Venetian blinds that you might have in your windows, but they can close or open, and by closing and opening, they expose different surface finishes. So you could have one that radiates heat or one that doesn't radiate heat, for example. On the left-hand side, you have just a picture showing multi-layer insulation construction. This is a product we make at RAL Space. In this picture, this insulation isn't well suited to being used on Earth. It's designed to be used in space, but there are some approaches which can make it better suited for working in a normal environment rather than the vacuum of space. So just to draw things to a close, we're exploring these opportunities to improve portable cold storage. I think that there's great potential for future work and collaboration. So this is the purpose, really, in my mind, about the scoping projects. The kinds of things we can be looking at in the future are more detailed thermal analysis. This, I have to stress, we have done a really basic thermal model. There is lots of scope for looking at detail. We can develop and test prototype solutions either in the lab or in the field. And I think cold storage comes up everywhere when you in vaccines, food storage, medication, and so on and so forth. So there are other solutions, there's opportunities for other products and other temperature regimes. And so looking at things that are colder than 10 degrees centigrade, for example. And just to finish, I think the SFN scoping projects are great because they provide a low-risk opportunity to explore these new ideas and bring together different viewpoints and expertise, creating this this sort of interdisciplinary discussion. It develops working relationships and opportunities that I wouldn't have had I not been involved in the STFC Food Network. So I will leave it there. Thank you.
Thanks, Brian. Thanks a lot for the insightful presentation. So there is some time for questions. So if you have any questions, feel free to raise your hand. Brian, if you can stop sharing your screen. So yeah, feel free to unmute yourself, raise your hand, or you can post your question on the chat as well. While people are warming up for the questions, I'll kick off with one very quick question. Brian, thank you for showing the different sort of opportunities that could be actually explored through space thermal modelings. So can I ask you, like, you provided, I think there were probably, if I'm right, around 8 different sort of examples of different covers or materials or possibilities of using different type of carrying material than just crates for tomatoes. So in this scoping project, would you be actually able to tell us something more in terms of how much savings or like, shelf life can be actually increased for tomatoes if we are using, let's say, newspaper covers versus multiple layer covers?
Yes, to an extent, I think.
Okay.
The idea that we're using here, we have this very simple model, and we have a baseline case, something that represents what is happening already, and then we're going to apply some of these modifications and see what that does to the storage temperature of the tomatoes. So I think in rough terms, we'll be able to give that sort of information, and the follow-on activities would be to really try and get into the detail.
Absolutely. No, that's very interesting to know. Thanks, Brian. And would you be okay to share your presentation with the audience here?
Absolutely, yes.
Thank you for that. Right, so if there are any more questions, feel free to use chat box, or we can take it towards the end as well. Just building on to this conversation, we now have our next speaker, Dr. Ramu, or Ramajanelu GV, as we call him, the full name. And he would be presenting about enhancement of shelf life of tomatoes using chamber for optimum humidity control. So Ramu, who is also a founder for Sustainable Center for Sustainable Agriculture in India, he's a director of that center and running that very successfully. One of the really good NGOs who are working substantially with farmers. So thank you, Ramu. We are very privileged to have you here as a speaker. Over to you. You're muted, Ramu.
Thank you, Sonal, and nice meeting all of you again. And this is a very brief presentation as part of the transition project. This was to try out a humidity chamber, a chamber which can control humidity and temperature, carbon dioxide, so that the shelf life of tomatoes can be enhanced. This was IIT Chennai and Linde were part of this project. And coming to the tomato, particularly in India, tomato is one of the very major vegetable crop in India. After potato, tomato is the largest area. Price fluctuations are very high. Always glut is in the market, and when the yields come and the price falls, farmers throws away on the roads. And these are pictures, and there will be millions of pictures if you actually search for tomatoes in India, kind of. And we regularly face this problem. And off season, the tomato prices goes up. Perishability is very high because of the very nature of the fruit. It's a climatic fruit. It requires proper storage conditions, and the aging continues even after harvest. To have storage, the difficulty is also that the cost will be very low. So storage also makes no sense if the cost is higher. So that's also is a major problem. So the tomato losses, tomato throwing out is very, very common. And India being a country where large food habits are only around eating their raw tomato or processed or cooked tomato, not using the processed tomato. So very little quantity of tomatoes which are produced or processed. So not much processing also happens. So one of the effort we try to do is how this can be addressed. The tomato perishability can be addressed. So a chamber is designed to maintain temperature, humidity simultaneously and look at what combination can help. And the chamber was designed and then an experiment was done and the results are out now. So we need to see how that can be used. And just to give a background, India has nearly 8,000 plus cold storages across the country with nearly about 374 lakh metric tons capacity, but less than 10% of it is used. Mainly because the cost of storage versus the gain for the people who are storing it, the cost price gain while storing, if you compare, it's not working out for the people. So they feel throwing out is much easier than actually storing because the price increase is not much there. So we need to figure out a cost efficient methodology, small scale units which can be used locally. And second, we also need to look at environmental friendly models as well. I think that's a combination which one need to look into. Particularly coming to the cost, one of the reasons we also have seen is we have large cold storage units and they try to manage for all at the same temperature and relative humidity, and the same thing is applied to all commodities which are stored in the huge chambers. So we were trying to figure out how this can be addressed. So with the help of IIT Chennai, Linde both together has designed this humidity chamber and is about 325 liters capacity, and temperature control was designed from 0 degrees to 60 degrees control with 1% efficiency, 1% variance it could be controlled. Similarly, 30% to 90% relative humidity could be managed, and each batch had about 25 kg which can be stored. So we try to look at from 18 to 31 degrees temperature and 25 to 70% relative humidity. So that was what was tried out of different combinations, and the results shows that around 22.78 degrees centigrade and maintaining the relative humidity of 61.7%. So at this temperature and relative humidity, the shelf life can be enhanced to about 12 days without any damage. Because tomato, since people buy raw tomatoes, the look also is very important. Look, and since it has a very thin layer, any over ripening opens up the tomato and then the damage is very high. So to control that and then to maintain the shape, maintain the color, maintain the fruit with intact, this seems to be an optimum temperature and humidity. And from this, in terms of going forward, we need to look at how first to publish this paper. The paper is being written, so we need to publish this paper. But it has an use only if we can make an application at the field, because we also need to look at the economics of it. How much economic it would be? Can the small chambers be designed? And what additional, like Brian was mentioning about the material change, whether that can further improve this chamber, that also we need to see. Then we can optimize and then put to use. I think that's what I see as a way forward. And till now, honestly to say, we have not yet tried in the field. This is only an experimental stage, but learning seems to be very promising. We need to take it forward. Thank you.
Thanks, Ramu. That was nice and sweet, very insightful as well, because we do need some of the lab experiments to be done before we actually try it out in the field. So that would be really encouraging to see what actually happens in field. And do you find, like, before I open it to the floor, I'm just forwarding my own question, but please feel free to, from the audience, if there are any questions, please feel free to write it on the chat box, or feel free to raise your hand. But so from Brian's presentation and your presentation, do you see the synergies coming together and how this can fit well with both of your work?
Yeah. From my side, I certainly see a synergy. If energy cost can be brought down by changing the material, probably it may become more cost efficient. So we need to figure out that part, because now we could optimize the temperature, relative humidity combinations. But if we can now look at material use, and then if we can bring down the cost per say per kg of storage.
Yeah.
5 to 6 days storage can solve the problem.
5 to 6 days of shelf life. Yeah.
The problem is in 1-2 days, farmer has to find a market. But if it can be extended to say 1 week to 10 days, much of the problem will be resolved, because the fluctuations are so high, and then it can also be transported. But today the problem is they only have to sell locally. In 2 days, everything will be damaged. So that I think will be a great use. So I think we should look at. That's why I was asking Brian if we can look at, if we can discuss further how this can be improved.
Yeah, to be honest, this is the purpose of this webinar. The purpose of this webinar is to start and initiate the conversation here, but don't finish the conversations here. We really want to build on to these conversations. And Hassan, I'll be giving the floor to you. Just 2 more minutes so that we have some sort of understanding of where this is going. So Ramu, you said that the optimum temperature is around 20 to 22 degrees, and that can have a shelf life of 12 days.
Yes.
Right. And that is found from the lab experiment that you have done. Brian, from your presentation, it appeared that, okay, we had the range of 15 to 20. So possibly if we are increasing a little bit on the temperature range, then hoping that, there could be a little bit of more leeway in identifying the materials that could actually bring down the ambient temperature from, let's say, you had in your presentation 32 degrees ambient temperature, but from my awareness, probably it can go up to 40 and 45 as well in, like, peak season, high summertime. So bringing maybe 10-15 degrees down with the help of different materials that you have, I think that can give a good sort of a combination of solutions to the farmers. And it could be low cost as well.
It would be,
Yeah, I agree with that. And just listening to Ramu's presentation, I think it's sort of clear that we've got different parts of the jigsaw, I think. So we need to sort of piece together all these bits of information.
Yes.
Yeah, that would be very, very helpful. Hassan, please introduce yourself and ask your question.
Sure. It's Hassan Bagheri. I'm from ADAS. My question is, have you looked at any other sort of gas? Because I think you mentioned CO2, but have you looked at any other sort of combination of gases like oxygen or other sort of combination that could be? Because I've seen in sort of fruit storage, they use a lot of this controlled atmosphere sort of storage, but I'm not sure why there's kind of nothing done in sort of vegetables. Is it the cost or anything else, basically?
No, the only thing which was measured was the CO2 emissions. Nothing else was done yet.
Yeah, so I think the question is around the atmospheric controlled environment or the packages that we have, a combination of the different gases. Is that so, Hassan?
Yeah, because I mean, for apple storage, I've seen that they sort of use controlled atmosphere storage, sort of for bigger storage, sort of for keeping the product for longer. I was wondering if there's you've done something similar with your chambers. Have you tried different sort of gas combinations, or was it just the temperature and humidity?
No, carbon dioxide is one which was tried out. See, the idea was not to look for a long-term storage, but it's an optimal storage. That's one part. Second, cost optimization was one of the major thing. That's why if there are storages available at 4 degrees, 5 degrees, 10 centigrade, cold storages are available, but maintaining at that temperature, shelf life increases, but the cost increases significantly. So we were trying to figure out what is that optimum temperature and relative humidity, where shelf life can be enhanced to about 10 days. So from 3 to 4 days to 10 days is a significant jump for the farmers, and then without adding much cost. So that was the whole idea.
Yeah, because for apples, you can have like maybe months for the storage. Yeah, but for tomatoes, for fastly moving goods, I think the solutions would need to be slightly different to what we would apply to premium foods. And apple is considered to be slightly borderline premium food in Indian.
Also, seasonal fruits, seasonal vegetables as well. So potato, for example. Potato will be stored for a longer period, whereas tomato will never be stored for a longer period. So that was the whole idea as well.
Yeah.
Thank you.
Thank you.
Okay, that's great. If there are any further questions, then please feel free to ask. Unmute yourself. This is or even if not the question, but just the comments, because we are just here for general conversations. So we are giving this an opportunity to interact and also share your experience. If you found anything interesting in your study or seen anything working somewhere else, then please feel free to let us know. We are here for knowledge exchange as well. Okay. Right. Yes, Franz, guys, if you want to unmute yourself, or would you like me to read it? Okay, so okay, that's fine. I can read it. So one of the participants are saying Sparky dryer in Uganda are electric powered dehydrator. So they have electric powered dehydrators, but they are too expensive, while traditional drying methods, solar dryers or open sun drying, do not work well during the rainy seasons and are much slower. The dryers start about $80 and can dehydrate 10 kg of mango in 2 hours, running 2 kg of biofuel. So these are some of the opportunities of, I think, the second life for the produce, which goes perishable within a few hours. I guess, Ramu, you also have some solar dryers in your
Yes, we are trying out. We are trying on a very now we are trying with about 16 cooperatives the solar dryers. They're really doing well, but again the consumption of dried products is very less.
Yeah, so it's also about the culture. It's also about the culture, the country in which the produce is grown. So in India, most of the produce, especially the vegetables and all, and tomatoes are consumed fresh. And when we say fresh, it's not just salads, but also in like making in curries and all. So yeah, that's the reason we might want to explore a little bit more in terms of how do we keep this tomato fresh for longer for the consumers, which is also going to benefit the farmers. But thank you, Franz, guys, for sharing it. Right, we now move to our third and final speaker, Emmett Rex from University of Aston University, and he would be presenting about sustainable cooling storage and transportation in East Africa fisheries. So Emmett, over to you, and you would like Paulina to share the screen, I'm assuming?
No, I can share my screen now.
Okay.
So, yeah, things back to normal. I'm just trying to find the right screen here. Yeah. Okay. Hope you can hear me now.
Yes.
I'll switch off the camera for a little bit to get a better stream. Actually, today I'm going to present about sustainable cooling and focus on transportation of cooling in East Africa, aquaculture actually, or fisheries sector. So let's talk about challenges first. So fishing is the occupation of almost 10% of Kenyan population. So we talk about 5.5 million only in Kenya. So 30% of the animal protein intake for Africans comes from fish. The post-harvest losses exceeds 50%. And fish post-harvest loss is smallholder farmers actually is even higher than 50%, which are the most impacted segment of fishing business actually. So it ends up actually fishing, although there is a lot of fish in the market, it is not profitable actually. So, and you can see here this video, the problem speaks itself actually. So this is how they sell fish in the market. So this wouldn't stay for a few hours and in warm days, which is normal in Africa actually. So the problem is we need cold storage, we need cooling transport, we need communication to see where the fish is available, where is the customer, and how to transport the fish from the supply to the end user. So if we simplify, actually, this is a cold chain. So this is a post-harvest. So transport in the first phase, we can have some processing and we can deliver directly to the market. It depends. And then these are the consumer actually. So when we did some field work in Africa, we found that the business actually don't have more than 10% access to cooling. So 90% needs cooling, but needs affordable cooling as well. When we looked previously, we tend to find that there is solution for stationary cold storages. It is not a big problem actually. Many technologies are there, and we listen today for Brian actually. And so cooling the storage is existing in terms of technology and in terms of controlling its operating condition. And the time now is to marry up different subsystems to make it more affordable and more profitable. So for example, we did some studies on running cold storage, absorption cold storage using solar heat and combusting waste, the agri-waste actually. There is combustion without converting it to biofuel, so which is the cheapest option we can do. And it works brilliantly actually when we integrate solar or bioheat with solar PV energy. But again, the problem is the transportation of cooling. So this is the idea actually which is funded by SFN, which is IoT cold box, which is Internet of Things cold box. And this cold box actually is to transport the cooling and focusing on fish transportation from the farm to the consumer or the sub-suppliers. And we have in this cold storage, in this cold box, sorry, it should be fitted with a sensor, and this sensor is communicated to the internet via application and Raspberry Pi control element, which is powered by a mobile phone battery. So the battery can work about 1 or 2 days without no problem. And because I am responsible for the cooling part, this would be the cold storage, the cold box actually for transporting the fish. As you can see, these are 4 sides. Each side represents a Coolth battery. So if you run out of cooling, you just replace it in the cold storage with a fresh cold Coolth battery. Each Coolth battery is filled with a PCM material, and this PCM material provides temperature below 0, suitable for transporting the fish from one point to another point. It can work brilliantly from the farm itself, whether you have a warm fish still harvested, or you need to transport it from a cold storage to another cold storage, or from another for the market itself actually. And this Coolth battery should be modular, one size fits all. Maybe if you need to mount it on a motorbike like this, if you have a small motorbike, you can buy one box. If you have bigger motorbike, you can buy more than one box. The modularity, it can be different actually. So this is a slightly bigger motorbike, so we can do a bigger Coolth battery actually to fit this big motorbike or big box actually, which is still under investigation with our African collaborator, which is the optimal size. So we are now in the phase of doing experimental work in the lab to quantify how much phase change material to be stored in these Coolth batteries. What is the optimal size? So this work is undergoing in our lab here at Aston. And then after doing this simple testing, we should manufacture this cooling box and transport to Africa to test it there actually. So and we're gonna simulate this Coolth battery with some ice pack filled with this phase change material, and we're gonna simulate the fish with ice pack, but at the temperature of the fish itself. And we have our colleagues actually will be responsible for integrating the sensor and link this sensor with the app to communicate the person who's gonna transport the fish, and this person can oversee, actually can see the fish demand, the fish source, and how much cooling he or she has in the box, and the state of charge actually, where they gonna charge the state of charge of the Coolth battery, and where they can swap the warm battery with a new fresh cool battery. So here actually in the market should be connected with the app because they request a specific amount of fish, and based on this signal they're gonna search for whoever ready actually, like Uber. So searching for a taxi to give you a ride, but searching for fish. And we have actually the fish store, the cold storage, or the fish farm if they have fresh fish available, so they can plug in this information into the application. So this is actually what we are doing now. And we are in the phase of testing the phase change material, quantifying how much material do we want to find the final dimension of the cold box and the amount of fish you can transport it in one batch, and which box we're gonna use actually. This is in collaboration with our collaborator in Africa. What is the impact of our work actually? This technology is to support sustainable food production and food supply chain resilience, maintain and create new jobs in fish or food supply chain, support fish sales actually, which is normally operated by women, which account for somewhat of 8.3 million in East Africa alone, and boost the income actually, because at the moment the income is not good enough, to be honest. This technology actually, it is simple technology, but we put everything together. It is not only useful for fish transportation, but can be used for vegetable, maybe small amount of vegetable like tomato, maybe big amounts, but if we can make this Coolth battery at bigger size, and vaccination or medicine transportation, which is becoming more important now. We need to deploy a vaccine at any point in time very quickly if we have any pandemic coming in the future, like COVID-19. So this technology will support this. It can also be mounted at small size in a drone. So instead of using a motorbike, you can use a drone, and it can be connected with, again, a storage for the vaccine and the transport from one point to another point. So the mean of transportation can vary. The application can vary, but what we try to do here is how to maintain the product cold enough, long enough, and communicate it with the supply chain, and whatever supply chain would be, food supply chain or medicine supply chain. So these are our team. Actually, it's a slightly big team. So we have Domitilla actually, which is a leader of the project from Africa, and myself, Ahmed. We have Luciano from business school working with One Tao. We have Tim and Bauson from Uganda, because we collecting data from Uganda and Kenya. And we choosing this location actually is very rich in terms of producing fish, because they have access to Victoria Lake. It's massive lake producing massive amount of fish. And we have Brian actually helping us, looking at Brian presented today, helping us today to find a proper, affordable insulation material to keep this cold box cool enough actually for a long time. Okay. That's it really. Yeah, just today is to share what we're doing, and hopefully collaborating with more people actually in the future. Thank you. And if you have any question.
Thanks, Ahmed. That was a really, really good presentation. Thank you for providing insights into your ongoing work. And yeah, so if we have any questions, please feel free to, Ahmed, if you can stop sharing your screen, please feel free to raise your hands or unmute yourself. We are here for discussions. But Ahmed, just before people warm up for questions, I have a few questions, just basic ones to just understand. So in terms of this Coolth battery, what's the general sort of a range of weights that we are looking at, like, you know, from smaller boxes to bigger boxes in general terms? So what's the range of that weight? First question. And the second one is like the shelf life or like the lifetime of this battery. So how long can we actually have if we have battery buying for?
Okay, so with the prototype would be around 1 meter by 1 meter. So this is the first prototype we're planning to produce actually based on this prototype we developed on CAD. Scaling it up or down based on the business actually need. That's
so
why we have
for 1 by 1 meter, like what would be the weight of that Coolth battery?
The weight. It's hard to ask actually, because it depends on the material filled in it. So we have some material now. The battery itself might weigh somehow around 1 to 2 kg, right? Yeah, but it been So we have some samples here we test, and once we get we choose the right material, we can give more accurate numbers actually for the weight of this battery.
Okay. And the lifetime of this battery could be?
Yeah, the lifetime actually, if we don't have insulation from Brian, it would be maybe 3 hours, 4 hours. If we have a proper insulation, so we're looking at optimally day long actually. So, but again, it depends on the point of transportation of the fish. If you transport the fish from a cold storage to the market, so you have already cold fish and you need to maintain its temperature.
Yeah.
If you have warm fish from the farm, this will drain the battery quite quickly, but not that quickly actually. That's why we doing lab test on what is the optimal material we can use. And actually it depends on the actual distances. So after doing the prototyping, the following phases will be obviously mapping the location of harvesting the fish and the location of the market, and then adjusting all the designs and the material with these distances.
Proper like a supply chain mapping exercise, because there wouldn't be one type of supply chains, because even in our project in India with Brian and Ramu, we found 7 different types of supply chains within a vicinity of 500 kilometers. So I'm assuming the complexities would be similar, if not more, in Kenya and Uganda.
But really actually this phase is we're trying out encapsulating the phase change material into this Coolth battery, and we try to communicate it actually, so get the sensor work and send signal out of this sensor, and try to do app for this thing.
No, definitely. I mean, to be honest, I can see this being applied to not just in fish produce, but other produce as well, and not just in one country. And as you mentioned, it could be used for vaccines and all those things as well, right?
Yeah.
In future, and could be applied in other countries. So yeah, variety of opportunities. To be honest, from a smaller prototype that we can actually get from this SFN project. That's great. We have one question. And what is the charging time of PCM?
Yeah, it's a very good question actually, because charging time could take 1 hour if you have proper fridge that can provide something around -5 degrees C. So this strongly depends on the cooling unit that can recharge this batteries actually. And the vision actually to have the stationary cold storage would be the same place you can swap your battery. So because it doesn't make sense to develop
Right.
many cold rooms, one for
Exactly.
storing fish and one for recharging the battery. So this is actually, yeah, it would be also part of the mapping. But yeah, if you have a fridge that can provide -5 degrees C, this wouldn't take 1-2 hours actually. So, and this is what we're studying now actually, the charging and discharging phase in the lab.
Perfect, perfect. We have some comments as well from, again, Franz Gois. Sorry if I'm pronouncing your name incorrectly. But charcoal coolers were constructed in Uganda to reduce on the post-harvest losses. Previously, farmers would harvest and keep their vegetables in their houses and some under the tree shade. This has changed with the building of affordable and sustainable charcoal coolers. The vegetable shelf life has increased from 1 to 3 days, allowing the farmers to store any extra vegetables that they have not been able to sold that day, identifying packing materials that address appearance, texture, flavor, nutrition value, and safety for vegetables has enabled better handling and reduced losses of vegetable quality during the transportation of markets. So yes, Franco, is actually to be honest, we don't want to be pumping quite a lot of fossil fuels to be saving food loss. So it's about the balance that we need to have here. So we are here looking into the trade-offs, okay, but in terms of, that's why when we say about sustainable cooling or identifying the alternatives, we are slightly going away from charcoal or other means of fossil fuel burning for cooling. So identifying the best possible sustainable cooling opportunities. Okay. And there's one question from Andrea. Will you assess whether dispersing and extending the cooling time could have unintended outcomes? Example, i.e. food waste being harder to trace, foodborne illness due to higher risk of cross-contamination, etc.?
No, at this phase, actually what we're trying to do is to maintain the fish transportation temperature long enough to reach from one point to another point. And in terms of looking at the consequences of not cooling the food enough, I'm an engineer, so we need support from other collaborators actually to look at this, how it would affect actually. Yeah, so
Yeah.
the people here.
Yeah, so I guess it's all about the primary objective. And as you already saw from Emma's presentation, almost like 70% of the food at the moment, fish is being wasted. It is not reaching to the right market. So it would be helpful to actually make sure that we have less losses across the supply chain and we have some sort of sustainable solutions. Okay, so Franco is, yeah, I mean, feel free to unmute yourself because you will be able to explain this better. He's suggesting that charcoal is not burnt, or water drips and seeps into charcoal wall, which has a cooling effect. Okay, I got that. Yeah, I might not have come across this. So thank you for sharing the link. We will definitely look into that in detail. Okay. Are there any other comments, suggestions, if not questions, comments for speakers? While we are here. Okay. If not, then I would really like to thank you all for coming to today's webinars, and I would like to thank Eric for hosting it on behalf of Gareth, and thanks to Paulina for really collaborating very well. Okay, well, I have one question. Have you tested the system with the beneficiaries likely to be women? So Ahmed, that's the question for you.
Yeah, we should send it out to be tested in Kenya.
Mm-hmm.
And in terms of gender, actually, Domitella, my colleague in Kenya, she is a woman actually, so, and she has access to wider network, including women in the market. So yeah, definitely would be part of our work. Yeah.
Yeah, and as you mentioned, I think probably more than 8 million women are involved in actually selling of the fish produce. So yes, if there would be like, you know, if this goes ahead and if the prototype is tested well, then there would be beneficiaries from proper like both the genders. And one more question: would you be able to attract private finance for upscaling the prototype?
Yeah, definitely. Yeah. So the next stage, when we test everything and we write the we get the right correlation between temperature, time, distance, these sort of things, we'll be able actually to find investment toward this prototype and upscaling it. And this actually what we do. So what we want to do is to make a real solution. It's not just for research purpose.
Yeah, absolutely. So once the prototype works, once we know the cost benefit analysis, I guess the next stage would be to find proper sort of investors to upscale the research and make it much more practically applicable across the.
And just actually to follow up on Sunal actually point, that's why I am as an engineer actually or researcher in engineering research, work with Luciano and Wan Tao from business school, is not looking at the technical viability, but the financial viability as well of the solution and how to tweak the solution to match the finance of the end user. So this is the main goal.
Perfect. Thank you, Ahmed. Would be good to produce a small video on prototype for communication. Yes, very good idea, Francos. Actually, to be honest, I have that in my agenda for hopefully March and April time next year, when we have a little bit of more insights from Brian, from Ramu, from Ahmed, to actually bring these learnings from different countries, from different produce together and see how the different solutions or similar solutions with a little bit of changes in the prototype can actually work across the different produce. So yes, we do have plans for video. So yeah, okay, this has been really great webinar, and thank you so much for participating from all the audiences. I think we have started the conversation here. What we are going to do is after every webinar, hopefully by next week or so, we would be establishing some sort of working group. And if you are interested in collaborating on working group, like, you know, writing let's say joint industry reports, papers, or collaborative grants, then we would be sending out this invite to all the attendees of the webinars. And if there is interest, we would definitely want to hear more from you so that we can work together, you know, for a common cause and for addressing common solutions and for this problem. Yeah. Okay. Right. So yes, and the recording will be available by next week from our website. The links would be also shared to all the participants who joined the webinar. So Any further questions? I'm here for the next 5 minutes. If not, I would really like to thank all the speakers who provided very insightful research, engagement from the audiences, and thanks to Eric and Paulina for hosting this. And thank you, everyone. Let's keep the conversation going. This is a very important area to be addressing on food loss and food waste, and it just doesn't have enough attention from all the different academics. So I guess it would be very important to bring forces together to address cold food chain across the different countries, and see if we could offer some sustainable solutions to the farmers who are at losses. So thank you everyone for joining, and looking forward to engaging with you through working groups.